In this video I'm going to give several examples of estimating definite integrals using a couple of different processes. A definite integral is actually a calculus concept, but we're going to be looking at algebraic estimations of this calculus concept. The definite integral is technically just the area bounded by a function and the x-axis. So really you're just finding an area created often by a curve, although it certainly doesn't have to be a curve, it can be a straight line relationship. Specifically on a velocity time graph, this area under the curve ends up representing the distance traveled. For example, this first graph here, notice this is a velocity time graph, and there's constant velocity. The constant velocity here is 40 feet per second. So think about it. If you travel 40 feet per second for 5 seconds, that means every one of those 5 seconds you travel another 40 feet. Well, we know that you can take velocity times time and get distance. And so really you can just take 5 times 40 and you travel 200 total feet. In symbols, the area under that curve between 0 and 5 seconds can be written as an integral. The integral symbol is really just a big S. It just means the sum of those blocks under the curve. So we'd say basically the area under the curve between 0 and 5 of function v in this graph right here. That's what those symbols mean. Okay. Now, you don't always travel at a constant pace. You could travel in a way in which you're speeding up for a while. You could keep a constant velocity. Notice this is a velocity graph, not a distance graph, so your distance would be increasing as you go at a constant velocity for a while and then you drop off. You could count squares. You could come in here and you could count approximately how many squares are on this diagram, and you could say, okay, I've got 1, 2, 3, 4, 5, I've got a 4 by 3. Basically there are 12 squares in this little set of blocks here. You could look at these little, these are little 2 by 3 triangles. So 2 times 3 is 6, divided by 2 is 3 is the area here, 3 is the area over here. Or you could use decimal values. You could say that that's about, maybe it's about half of a block, maybe it's about 0.4 blocks, maybe that's about 0.8 or 0.9 blocks. You could add those up. But 3 plus 3 plus 12, that just adds up to 18 square units. Now, you have to be careful. 18 is not the correct answer here if I wanted to find this integral. The correct answer here would actually be to consider the fact that these are 1 by 5 blocks. So I have 18 1 by 5 blocks. Each area is 5, and so I'm going to have to take 18 times 5. That's 90 square units of the graph. If you notice, the dimensions of the block are feet per second by seconds. And so if you multiply feet per seconds by seconds, the seconds cancel, and you're left with feet, and you can see that that's a distance. So unlike the average rate of change or the instantaneous rate of change where you're finding a slope and dividing, when you're finding the area under the curve, you're actually multiplying your 2 units together. And that sometimes helps you figure out what you need to do in these problems. You could also, if it's a shape that you know how to find the area of, you could find the area using the area formula. So for example, that's a trapezoid. Its area is half the height. The height here would be 15 times the sum of the bases. One base is going to have a length, looks like, of 8. And the other one, 1, 2, 3, 4, height of 4. And that's going to be 90 square units. Again, in this problem, it's not square units, though. It's really feet per second times seconds, which works out to be 90 feet. So, again, you can look at these a lot of different ways.